A seemingly impossible problem that cleans up really nicely. Let's simplify until we find a solvable problem. We'll build our calculus intuition about slopes of slopes. We'll bring in some ideas about transformations of graphs, and then poof, a certain number that we're becoming friends with will pop out. Let's jump in. Our goal is to find the ratio between the slopes of a 6-degree polynomial. And from what we know about polynomials, there will be at most 5 extrema, which means at most 4 spots in between those extrema to compare. So we have 4 spots to find and compare on a polynomial that has up to 7 coefficients, right? 1 for each power. It's a constant, and that sounds pretty unmanageable to sort through all the cases. But the problem statement does give us one major simplification, and that's symmetry. So that means not only can we eliminate all of the odd powers, because only even powers are symmetric, which is closely related to what you see on screen here, what we call an even function, where the negative values produce the same output value as the positive values. But also we can reduce the number of points that we need to check from 4 down to 2, because any value that we find below 0 will be mirrored on the above 0 side. So my first thought was to rewrite the expression in this simplified case, but then I thought a little bit more about where we're headed. So this idea in calculus called the derivative is how we find the slope. If we're looking for the largest slopes on an interval, a certain range of values, well then we need to take the derivative of the derivative and set that equal to 0, because if we graph the slope, right? So imagine that this is a picture of the slope itself, right? So not the original function, but a picture of the slope. Then the maximum of that is going to give us the point where the slope is the steepest, as well as, in the reverse case, it'll give us the slope when it is the most negative. And fortunately, that works out really well, because the question asked about magnitude, so we don't care about whether the values are positive or negative. So we're basically looking for the maxima and minima of an expression that looks like ax to the 6th plus bx to the 4th plus cx squared plus some constant d. And at this point, I realized that we can do even better than writing a polynomial with the even powers. So what if we wrote down this derivative of the derivative, the second derivative, in terms of the places where it has a value of 0, because that's what we're aiming for, right? And that expression is actually really easy to write. And the reason why is because that's kind of the whole idea behind why we factor, right? Because if any one of these factors is equal to 0, well, then the whole product of all of them is 0, right? And so the 4 solutions to this polynomial expression that's been factored are x1, x2, x3, and x4. And actually, we can do even better than that, because we know we have symmetry. And so not only are we going to have these x1 and x2 values, we're also going to have their negatives. And so the way I'm going to write that is negative x2 will become positive x2, and negative x1 will become a plus x1 here. And so we've taken something that seemed really nasty, and we've managed to kind of clean it up. The other nice thing about this approach is that we won't run into the situation where we would only have 0 or 2 solutions to the second derivative, neither of which are very interesting, right? If we have 0 solutions, well, it's just a single bowl shape, right? And there are no intervals to even compare. If we're talking about a symmetric with only 2 intervals that we need to compare, well, they're going to have the same slope by symmetry, and so the answer to our question would just be 1. So now we need to use what we know about expanding polynomials to address this particular situation. So we have x1 and x2 each showing up twice, and so those are actually differences of squares, and so we can write this as x squared minus x1 squared from the 2 x1 terms, and then x squared minus x2 squared from the others. Again, we're targeting this being equal to 0, although that part doesn't matter too much. And then if we expand this, we get x to the 4th from those leading terms. I'm going to group our terms that we get that are quadratic in x, and so we represent that like that. And then finally, the negative signs cancel out, and we get a trailing constant term, again, all set equal to 0, and we go from there. Okay, so now we need to think about finding the ratio of slopes. So what we'll need to do is we'll need to find the first derivative, which is going to require us to reverse the power rule, because remember, we're coming from the second derivative. So if you're not familiar with this rule, you can find the slope of any point on a polynomial by reducing the power by 1, that's this n minus 1 that shows up here, and then multiplying by the original power, that's the n on the front. Interestingly, we don't ever actually need the original function itself, and then we can sub in our values into the first derivative and find the ratio of the two. So it's going to get a little bit ugly, but let's do the integral here. So we're going to increase the power by 1 and divide by our new power, because that's the exact opposite of multiplying by our original power and decreasing the power. So you'll notice that if I brought the 5 down, it would cancel the 1/5, and we would reduce the power by 1, and we would have x to the 4th. And since we're trying to undo the process of doing a derivative, that's exactly what we have going on here. And I like focusing on it from the perspective of thinking about the power rule for derivatives, because that is itself derived from an idea called the difference quotient, which kind of connects it more tangibly to what it is that we're doing here. All right, so there is our first derivative. I will label this f prime of x. And then what we can do is we can substitute in the values of x1, and we're also going to substitute in the value of x2. And for the rest of the video, I'm going to do some kind of intermediate calculation skipping. This result spits out negative 2x1, that's cubed times x1 squared minus 5x2 squared, all divided by 15. And we get a really similar result because of symmetry, right? There's no actual difference between x1 and x2. And so you'll notice that these formulas are kind of interchanging the position of the x1 and the x2. So now let's find that ratio, and I'm going to drop it all in an absolute value because the question asked about magnitude. Okay, so we don't really care about the positive or negative sign on those. And about the only thing that cancels here is the leading negative 2 and the trailing divided by 15 on each of these. So this expression just becomes x1 cubed multiplied by x1 squared minus 5x2 squared. And then kind of by symmetry again, we can kind of guess at what the denominator would be. I'm not actually doing any guessing here. We have the explicit formula. We calculated it on the last slide where I was writing. Okay. And then at this point, I noticed something interesting, right? If I were to expand this, I would have an x1 to the 5th in the numerator and x2 to the 5th in the denominator, but then the other terms that I would produce would also be sort of raised to the 5th power in an interesting and kind of indirect way, right? Because we'd have x1 cubed times x2 squared or vice versa. And so that motivates me to do some sort of a substitution. So the idea of parameterization is really powerful because it allows us to simplify cases that maybe it's a little too hard to think about that ratio. And so what I notice in our particular case is that if I use a multiple one of the other, that everything will kind of cancel out and clean out really nicely. And so I'm going to make the substitution that x2 is equal to k times x1. And when I substitute, all those x1s are going to end up canceling out, and we end up with the expression 1 minus 5k squared all over k cubed times k squared minus 5. And you'll see some of the same structure there in that expression as the expression that we had before that. Just a bunch of x terms have all canceled out. And now this is what's called a rational function. It's a fraction of polynomials. This family of curves are fairly friendly to work with. We mostly just need to look for the interesting values, which would be where it equals 0, which is when the numerator is 0, as well as when the denominator is equal to 0. So the numerator, 1 minus 5k squared, equals 0 when k is positive or negative 1 over the square root of 5. The denominator equals 0 at k equals 0 because of this leading k cubed term, as well as the positive or negative square root of 5. Okay, and so now we have some different intervals that we can look at and try to determine whether there's anything significant about these breakpoints, and then from there we'll be able to do some final work on identifying some interesting things about k. Think about each of those things on a number line, and I'm only going to start from 0 because we're dealing with symmetry, right? And so we don't really need to worry about those negative values. And it turns out that based on some conditions of the problem that have to do with the way that we set it up and taking the power rule for integration, it actually turns out that on this intermediate interval, the relationship just doesn't hold. And so really we're only looking at small values of this ratio and large values. And because of symmetry, you could really think of this as really only one of these two intervals containing all of the possible values that are our ratio between x1 and x2. All right, so for example, if we punch k equals 3, which is just a little bit bigger than root 5, so should give us a fairly clean value, it spits out the value 22 over 27. And so what we're saying there is that f prime at x1 is 22 over 27 times f prime at x2. Yahoo! Not all that exciting, right? But what is interesting is what would be the case where f prime of x1 and f prime of x2 are the same value. And so that's what we want to look at. So we're going to set the fraction that we got, 1 minus 5k squared over k cubed times k squared minus 5. And we're going to set that equal to 1, okay? And we could set this on an absolute value as well and deal with the positive case and the negative case. Not much interesting actually ends up dropping out in those two different scenarios, mostly because the k cubed term here will dictate the sign. And so we would have to just deal with the negative values of x in order to have this absolute value come into question. All right. And so what we could do is we could bring the denominator over to the right side, distribute that k cubed, bring all the terms to the same side, and we would have a polynomial that's k to the fifth. Because of the trailing coefficient being a 1 and some of the setup of the problem, I'm suspicious that 1 would be one of the solutions to this expression. It actually does end up being one of the solutions to this expression. But even if you factor out a k minus 1, you still have a fourth degree polynomial that's left behind, and so you're probably punching it into an integral calculator. It turns out that of the 5 solutions that we know we will get to a fifth degree polynomial in the complex plane, 3 of those are real, okay? So 2 of them are imaginary, involve imaginary numbers, don't get us any closer than what we want. And then the remaining 2 solutions are 2 minus the golden ratio and 1 plus the golden ratio. And you might have seen the golden ratio coming, right? You saw square roots of 5. That should maybe make us say, hey, wait, I bet the golden ratio is coming, right? All right. So what are these values? 2 minus the golden ratio is about 0.38. The golden ratio itself about 1.62. So if we add 1 to it, we get a value approximately 2.62. And the golden ratio, it's just so cool. Not only are those numbers both involving the golden ratio, they're actually reciprocals of each other. So we don't even end up with 2 distinct results. We really only end up with 1. Because remember, x1 and x2 were kind of symmetric with respect to each other. Didn't really matter which one was which. And so if you reciprocate them, that's just a matter of kind of switching the positions of x1 and x2. Pretty neat that even though there's a 1 and a 2 involved there, a positive and a negative, that they end up being exactly reciprocals for each other. All right, so that's a wrap. I'd encourage you to go integrate that expression that we had for the derivative one last time, and then substitute in the values of that align with k that we just got there. So say 1 and 1 plus phi for x1 and x2, and take a look at it on some sort of graphing calculator or online tool. Sure enough, you'll see the result that we were hoping for drop out. The slopes at the steepest point on each of those intervals will be the same as each other. I'd also love to expand this problem by trying a fourth degree polynomial that's not symmetric, so you'd still have only 2 primary intervals that you're dealing with. We could take a similar approach and see if we can find some of the same kind of results drop out, maybe totally different results drop out. Without the symmetry, all bets are off, right? It's probably not going to be the exact same results. It's probably about the same as this case, messy, but doable. I like to strike that kind of in-between spot, something that pushes us to do some new problem solving that maybe we haven't come across before, but also is within reach, right? It's not this long drawn out series of calculations or something that requires way too much computation or insight in order to get through. All right, that's all for now. As always, let us know your thoughts.